Hi students, welcome to the session on vector magnetic potential A. Right? We know that in a electric field the source is scalar charge, right? So it has only magnitude, hence it produces only scalar potential V. But in magnetic field the source is what? Vector, current element, IDL. So it produces both scalar magnetic potential and vector magnetic potential A, right? So since our source is a vector, it is necessary to add the information about the direction of the source, right? Which is contained in the potential, right? So direction of the source to be included in the potential also. Okay, so vector magnetic potential is represented with the symbol A, right? And it should vector magnetic potential should contain either B or H, magnetic field or magnetic field intensity, as the spatial derivative. Okay, since we have to find the change in every direction, it should have spatial derivative of B or H, right? So we have two spatial derivative operations. One is divergence of that vector, another one is curl of the vector, right? Because we are going to have a vector magnetic potential, right? This should contain B or H. So B should be divergence of some A, or B should be curl of A, but we take only curl, we don't take divergence, because curl of A only will give vector, right? Divergence of A will give scalar, but our field is a vector. So what we do is we write vector magnetic potential in terms of magnetic field as B is equal to del cross A. This is giving a vector quantity as output. That's why we took curl, not divergence. So here you see this is a relationship between the vector magnetic potential and magnetic field, right? So that is very important one, right? Like we did a relationship between the scalar magnetic potential and magnetic field, H is equal to minus del Vm. Clear or not? This is magnetic field density, this is magnetic field. You see what is the unit of B? We know unit of B is Weber per meter square, and the unit of del is 1 by m. So what should be the unit of vector magnetic potential A? Meter cancel, it is Weber per meter. So the unit of A is Weber per meter. Very important. So next thing we have to remember is, if you know the vector magnetic potential A, from that we can find B. That's what this equation tells you, right? This A can be obtained if we know the current distribution, ideal, how ideal is distributed, right? So from current distribution, we can find vector magnetic potential. From vector magnetic potential, we can find magnetic field. This is the concept used in radiation, in antenna, right? That's why the concept of vector magnetic potential is very important. So how to find the magnetic field in free space? When current flows through antenna, you find vector magnetic potential. From magnetic potential, you find magnetic field. What is the relation between A and I? That is given here. So the vector magnetic potential A is given by integral L mu naught ideal divided by 4 pi r if it is a line current, right? So if current is line current, ideal is you can get A from this equation. Similarly, if it is a surface current, A is given by S mu naught k dot ds 4 pi r. This is surface current, right? Similarly, A is equal to volume mu naught J dV by 4 pi R, volume current. Okay. So from current distribution, find magnetic potential. From magnetic potential, find the magnetic field. Okay. So that is very important. This is the concept used in the antenna theory. Right. That's why vector magnetic potential is very important. Next, we know Gauss law for magnetic field is given by del dot B is equal to 0. If del dot B is equal to 0, as per null identity, B can be written in terms of del cross A. If you have any doubt, please refer my video on null identity, which is dealt in chapter number 1. So B is equal to del cross A. Right, now I write substitute B is equal to mu H. So H, that mu I bring that side. In free space it is mu naught del cross A. Free space. In free space only I am going to find a magnetic field in the antenna application, right? So H is equal to 1 by mu naught del cross A, right? And if you take curl on both sides, del cross H, right? Right hand side you take curl, del cross 1 by mu naught you bring that outside, 1 by mu naught del cross A. We know del cross H, left hand side you take curl, right hand side you take curl. Del cross H is equal to J, that is equal to this one, right? So what is the next thing we have to know? We have known one vector identity, del squared A is equal to del into del dot A minus del cross A, right? So in this equation, it is a vector magnetic potential A, del dot A is equal to 0. Magnetic potential. Why? Because in a magnetic field we have only steady state current, steady state or DC current. DC means constant value. If current is steady, you see from the equation, if current is a steady state current, right, the magnetic vector magnetic potential also steady state. That means A is also a constant. So divergence of A, that is del is nothing but dou by dou x, change of A is 0 because it is steady state. Steady means no change. Del means dou by dou x of constant. Dou by dou x constant means 0. So del dot A 0. So del squared A is equal to, what is del cross A? You see from this equation, del cross A is equal to mu naught J. This mu naught. So this is minus here. So minus del cross A is it mu naught J. What is this? Have you seen this equation already? Fine. Mu naught J vector, right? This is what you know as Poisson's equation for magnetic field, because we have already studied one equation, del square V is equal to rho V by epsilon minus, this is Poisson equation for electric field. You see this is Poisson equation for magnetic field, right? So you can say this right hand side vector, left hand side is also vector, because gradient will be a vector parameter. So don't think that it is a scalar, it is a vector. So minus minus, here 1 by epsilon naught will come, that is for magnetic electric field permittivity, magnetic field permeability. So beautiful equation. The relationship between the electric field and magnetic field, right? So what is the thing we are understanding from here? Vector magnetic potential satisfies Poisson equation, whereas scalar magnetic potential satisfies Laplace equation, del squared Vm 0. Similarly, scalar electric potential also satisfies Laplace equation. We have studied all the things, right? This we studied in electrostatics. This is what we studied already in magnetostatics. Okay, so wonderful equation. Next thing we have to remember is, we know pi is equal to closed integral B dot ds. Electric flux, magnetic flux, I dealt here, right? So pi is equal to B dot ds. This is surface integral. I write in terms of line integral. I know B is equal to del cross A dot ds closed integral. So if I want to write in terms of line integral, what I have to do? I have to use Stokes theorem. So if I apply Stokes theorem, this will be equal to, what is that? Stokes theorem relates the surface and line integral. Del cross A dot ds is equal to integral A dot dl line. So that is equal to phi. So this implies phi is equal to A dot dl. Fine. So this is another one important equation. So what it is telling, the line integral of magnetic potential around, it's a closed path. Since it is a magnetic potential, you use a closed path, right? So sorry, right? Stokes theorem relates open del cross ADS. I write these. Okay, sorry. Here I can write del cross A. If I apply Stokes theorem, surface integral, it will be a closed line integral, right? So if open surface, if I take open surface, it will become a closed integral. So pi is equal to A dot dl. So from this, what I understand, here I understand the line integral of vector magnetic potential around any closed path. You see, this is a closed path is equal to the total magnetic flux, which is passing through a surface enclosed by this curve. Right? This is what this equation is telling. You see, this is equal to one more equation we studied in electric field. E dot dl is equal to 0. Right? So this is more or less similar to that equation. Right? This states that what is the thing? The line integral of vector magnetic potential A around any closed path. You see, this is line integral, this is line integral dl. So closed path is closed path around the closed path is equal to what is phi? Flux passing through surface. Flux passing through the surface which is enclosed by this curve, which is enclosed by that path or curve. This is what this equation is telling. Right? That's all about the vector magnetic potential. Thank you.